Okay, we'll get started. This presentation is going to be recorded, so this is going to be shared on our website after the fact. So if you miss anything or have to jump early, you can always access it and view it at another time. So today's presentation is commercial HVAC system fundamentals. We'll be going over some basics and how to apply heat transfer in the HVAC industry. A little bit about myself. My name is Jack Corcoran. I work at Cadent Energy Solutions. We are an HVAC sales representative firm. We're based out of New York City, and we do work all over, the tri-state area. I went to school at the University of Notre Dame. I got my bachelor's degree in mechanical engineering. Go Irish. I actually have my PE in 3 different states. So I'm licensed in New York, New Jersey, and also in Texas. So, and the last thing is I started my career at CMTA when it was actually AMA Group USA. I was a mechanical design engineer before I switched over to HVAC sales. So if you're wondering how I have a PE, that's my origin story. A little overview of what to expect with this series. This is just part 1 of many presentations that we'll be doing weekly. Just the main idea that we wanted to do is to provide you guys an educational series. We timed it up in the summer, so if you have summer interns, this is probably a really great resource for them. Give them an hour to do something while they're eating their lunch, and we'll go over a lot of fundamentals. So we're going to introduce specific HVAC equipment. Every presentation is going to be dedicated to one type. We're going to dive in to the components, explore how the heat transfer and the physics applies to each component and how that actually works. And then we're going to switch over into design side of things and say, what are the pros and cons of this type of HVAC equipment? And then, which projects do it work best in? So that's just a high level overview. This week is a little different. Today, we're talking about just fundamentals and an overview. So we won't have one specific piece of HVAC equipment. But next week, we're going to talk about VRF fundamentals. And the following week is going to be rooftop units. So this is a little roadmap. And you can expect next week that we'll be talking about VRF and diving into that. So without further ado, today's presentation, I'm going to start it off with a promise. 4 things that we will cover today and you will be able to do by the end of the session. First is you're going to be able to describe how HVAC systems apply the principles of heat transfer, the laws of thermodynamics. Second, we're going to talk about the fundamental system loops introduced by Trane and their air conditioning clinic. So if you've taken that, this might look a little familiar. Third, we're going to ask the right questions. We're going to look through the constraints of each project, an example project, to kind of demonstrate what the process looks like for selecting different types of equipment. And lastly, we're going to just match the constraints to a piece of equipment. And as I said, we're going to have a few examples at the end. So a fundamental concept of HVAC and our industry is that we are trying to move heat into or out of the commercial space. This is fundamental. It is core to every piece of equipment that we put in our buildings is going to move heat in or out of the space. In order to actually make that work, we need to know how does heat move on its own. So the laws of thermodynamics are, you go back to your days in school. These are fundamental to and applied every single day in our industry. The first law says you cannot destroy energy, right? It can only be transferred or transformed. For us in practice, this means that when we remove the heat from one space, we have to actually move it into another one. Our I love pictures, so there's gonna be a lot of pictures in this presentation. So, icon 1 to 2 or vice versa, 2 back to 1. You can't just wave your magic wand and poof, your heat is gone. It actually has to move somewhere else. And the second law of thermodynamics, heat flows spontaneously from hot to cold. And if we want it to move the other direction from hot or from cold to hot, we need to apply work or input energy in order to do so. So if we want to move against the energy gradient, we need to actually put in work. And these icons here, I kind of like to think about it like a ball rolling down a hill. The heat is going to transfer downhill if it's hot to cold. And then if we want to push it up the hill, we have to put in work. So this is just two of the fundamental laws that explain how the heat works. So we need to figure out how we can apply that. Now for us, we have an occupied space and we have the outdoors. This is the two most common places to reject our heat and our heat sources, right? We have our occupied space that we are trying to maintain a certain temperature in, and the best place to reject or absorb that heat is from the outside. So if your indoor space is 80 degrees and your outside space or the ambient air is 60 degrees, the heat is going to naturally flow from indoors to outdoors, and that's great, right? And if this were the case all the time, we can just open a window and none of us would have jobs. The industry would just be windows that you can open up and close, and that's great. We can use this for free cooling in many parts of the year. If you've heard that term, we actually do apply this quite often for energy efficiency. And it works in reverse. So if it's hot outside and it's colder inside, the heat's going to flow in. The issue with this is that it could get very hot in your space. We need a temperature that's colder. How do we actually move the heat against the gradient? As we just said, we need to put in work. This is the cornerstone of our entire industry. We are tasked with figuring out ways to move that heat against the gradient. We want to cool a space that is actually colder than outside. And how do we do that? We got to add in the machine, so to speak. We got to put in the work. So we still have our two spaces. At the left, we still have the occupied space, and at the right, we still have our ambient outside temperature of 95. But what does it look like to add in the work? What does that mean? How are we actually accomplishing this heat transfer against the gradient? It's actually a little bit more simple than that. Instead of just a one-step process to move the air directly to outside, we have to have an intermediate step. It's now two parts. We're going to move our heat from our 75-degree indoor space to a colder coil, because we know that heat moves naturally from hot to cold. We'll move that heat from 75 degrees space into a 45-degree coil. And then we need to figure out how to get that to reject outside to 95. If we add in the work, we can heat up that fluid. In this case, we have refrigerant. We're heating up the refrigerant to 115 degrees. And then we can reject from hot to cold, right? Our 115-degree temperature is going to be able to reject naturally into a 95-degree ambient temperature. So that adding in the work and adding in the machine is really just adding in an extra step that allows us to get temperatures that achieve a hot to cold and then hot to cold again. The tool and the mechanism that we actually use is called the refrigeration cycle. This is a cycle. We want to make sure that once we use that refrigerant, it's 45 degrees, it becomes hot. We want to actually make it cold again so we can keep on reusing it. It's a loop, a continuous loop. And so that's actually the refrigeration cycle here. There's 4 components to it. Today, we're not going to dive into it. More importantly, I just want to show you the temperature gradients, and the compressor is actually the portion of this cycle that is adding in the work, right? We have that 45-degree temperature refrigerant. If you add in the work at the compressor, you're going to change it to 115 degrees. So you have your hot and your cold side And that just continuously cycles in a loop in order to continuously reject your heat to your outside. All right, so now that we finished section one, we just covered some heat transfer basics. We're going to dive into the 5-loop framework. As I said, these are 5 of the system loops that Trane's air conditioning clinic states. And, you know, there's not very many ways to go about it. We're giving Trane all of the credit due because this is an excellent way to understand how we achieve the heat rejection, right? In the first section, we learned that we need to move heat outside, but how do we do that? Each one of these loops allows you to move heat from one portion, from 1 to 2, essentially is what it is. They are airside, chilled water, refrigeration, heat rejection, and controls. Now, controls isn't exactly moving heat, as we said, but it is still a fundamental loop that allows all of the other 4 to operate as a single unit. So every piece of equipment that we're going to be talking about through the whole series is going to be mapped back to one, 2, or multiple of these loops. Every piece of equipment can be mapped back to this. The first loop is airside system. How are we moving the heat? The heat is generated in the occupied space, and we need to move it out. So the airside system uses air in order to create that cycle, create that loop. We are pumping in cold supply air into the space where it is absorbing the heat. It then leaves the room as return air. A fan pulls it over the cooling coil and rejects the heat into the next loop. So then that warm air becomes cold after it rejects the heat, and it cycles back into the space. Your cold air absorbs heat and then rejects heat into the coil. We just talked about on the previous slide the refrigeration cycle. This cooling coil can contain refrigerant, as we were talking about, or it can contain chilled water. Those are 2 of the main HVAC mediums that we use to reject heat in this airside system loop. I will say there is another portion of the airside loop that involves mass balance. So if you don't want to pressurize your space, you need to think about your outside air and your exhaust air, sometimes called relief air. You need outside air per code and ventilation. So you need to have some way for that overpressurization to be relieved. The mass balance is at the bottom, but the main focus of this airside system loop is that we are transferring heat from the occupied space into a cooling coil via air. So the next step, we just saw that we rejected heat into a coil, right? And so if we don't have refrigerant, we have chilled water. This loop carries heat between the cooling coil that we just saw in the airside loop and into your evaporator. This system loop utilizes chilled water. We're pumping water into a coil, into the air handler or the fan coil, and that is where it absorbs the heat on the left side. Our chilled water becomes warm, which is our chilled water return, and it goes back to the evaporator where it rejects the heat into the next system loop. And by rejecting the heat here, it becomes cold, chilled water supply, and then it goes back to the cooling coil. So as it is with the airside loop, your return is warm and your supply is cold, and it continuously operates as a loop in order to operate efficiently. An important thing to know in this system, the evaporator is a water to refrigerant type heat exchanger, right? So we're rejecting heat from our water into refrigerant. And so that leads us to our next loop, which is the refrigeration loop. The evaporator is on the left side here, as we said. That is absorbed from our chilled water loop. As we said, this refrigerant system loop is just the refrigerant cycle, as we showed earlier. There's the 4 components. We'll dive into that next week when we talk about VRF systems. But for this presentation, we'll just talk about how it moves heat. So In the evaporator in the refrigeration loop, it absorbs the heat from the previous loop. We're going to absorb the heat from our cooling coil. It's a water to refrigerant heat exchanger. Water rejects the heat into our refrigerant. Our vapor, which is our return in this situation, is hot. Hot vapor goes to our condenser where it rejects the heat and turns into liquid. All that refrigerant heat gets transferred to our water loop in our condenser onto the next loop. So as you can see, it's another loop where you have a hot side and a cold side, and you're just moving heat along from one to the next. Same thing here, our heat rejection system loop. We absorbed our heat from the refrigeration cycle, and it's now in water, right? So this is our condenser water. These are linked with cooling towers or with adiabatic coolers or dry coolers. Our condenser water absorbs the heat from a refrigerant and rejects it into the ambient air. This is the portion where it's an extra step, right? We're adding an extra step to pull that heat from the refrigerant cycle into the ambient air. We need water to do so here. In this situation, the liquid cooler, as you can see on the right side, is located outside, outdoors, because we are rejecting that directly into the ambient air. And our heat exchanger on the left side, the condenser, is located indoors with the refrigerant cycle. And the last loop, as I said, it's not for heat rejection. It is actually a control loop. It is the brain behind the whole operation. Our central controller communicates between these loops to allow you to create complex sequences, essentially allowing you to be flexible. If we had a system that was only operational on the hottest day of the year, what are you going to do in September when it's like 65 or 70 degrees? You're going to be wildly inefficient, or you're going to be overcooling your space. There is a control loop built into all these systems that allows you to dial in better control, become more energy efficient. Whatever system and goal you have, it allows all of them to operate together as one single system. And we want to be as efficient as possible. You don't want to waste electricity. You don't want to spend lots of money for your clients and your end users and owners. They're trying to save money, and you want to provide a system that can actually do that for them. If you have a control system, you can really dial in exactly where you might be wasting heat or wasting energy, and that's a very powerful tool in 2026. The digital era of the Internet of Things is important. So BMS is the most common way you see this control loop integrated. So this is all 5 of them laid out together. As you can kind of visualize it as heat moving. I mean, go back to our other slide before where we had just our occupied space on the left and the ambient air on the right. This is a much larger complex system, but you are still moving the heat from the left side of the diagram all the way through your 4 loops into your ambient air, and it's all controlled with the control loop. All of the HVAC equipment and systems that we'll be talking about actually will be using 1 or 2 or multiple of these loops in different combinations in order to best fit the project needs. So not every project is going to need all 5 loops. As you can imagine, it's more expensive, it takes up space, and you might not need that in a small little apartment. So this is the wide out view lens. We can dial it in and go with 1 system loop, 2 system loops, whatever combination works best with the project. So a couple quick examples. So 2 loops, an example of a 2 loop system is a window unit. This is a PTAC. It just sits underneath your window in hotels. You've probably seen these before. All it is an airside loop and a refrigeration loop, because you're providing your supply and your return air, right? You're pumping cold air into your room. And the way that it's achieving that is with the refrigeration cycle. You have to add in the work because these things have to operate when it is warmer outside than it is inside and you need cooling. A little bit different way to use two loops is the package rooftop unit. With the window unit, it sits right in the room. It only serves one room. There's no duct work. With a package rooftop unit, you can use duct work to move your air greater distances, or even into multiple rooms. So this becomes a powerful tool when you have a couple different rooms that may need different amounts of air to cool it properly, but you still need to reject the heat somewhere, right? You're still rejecting your heat from your air side into your refrigeration loop. You just throw a rooftop unit on the roof, and you have two loops, and it's a very simple system. And the other end of the spectrum is five loops, right? You have a central chilled water plant and a complex control system. You have a cooling tower, a water cooled chiller, and you have air handlers or fan coil units in your space. This is reserved for campus level projects or large buildings in very high heat loads and tonnages, because the only time you want to spend all the money for something this complex is when you really need energy efficiency, large systems, and a good way to control all of it from a central location. So these are kind of the two ends of the spectrum here. So we just went over the 5 system loops. We're gonna next go into the project constraints. What drives which pieces of equipment we want to pick? Which heat transfer loops do we want to use? So as we said, going back to the beginning, we have the occupied space and the ambient air, right? We're moving the heat from the occupied space into the ambient air, and we just have to figure out a way to do it. And our tools that we can use are listed at the bottom of the screen: air side, chilled water, refrigeration, heat rejection, and controls. Here's just a bunch of pictures of different types of equipment. If you're trying to think, where do I even start? The good thing is there's lots of options. The bad thing is there are lots of options. So, we got to narrow it down a little bit. Otherwise, you're going to be wishy-washy. You're going to, be overwhelmed with the amount of things you can put in your building. But the good thing about all these pieces of equipment is they all have their own strengths and their weaknesses. So, for a given project, you can quickly narrow down which pieces of equipment are not going to work. These are 10 of 10 of the important constraints and questions we want to ask ourselves when we are deciding which piece of equipment we're going to use in a building. If you walk through any specific project and you ask yourself these questions, you might even end up with only one option, which is going to be great. You don't even have to think about it. You might just say, we have to go with PTAX, or we have to go with the chilled water plant because there's no other way to do it. So kind of running down the list here, the distance to the heat rejection point. So if you, as I said, if it's a single room that is a perimeter room, you could just open a window. That would be the best, easiest solution. But we all know that living in New York, we have to be able to transfer that heat in the summer and use cooling. So a PTAC might work great for a single perimeter room, but if you have an interior room or something's located in a basement, you have to figure out some way to get that heat somewhere else. So, ductwork, refrigerant, chilled water, condenser water, those might force you to use extra loops if you have to transfer that heat a long distance. Footprint and equipment location. If there are mechanical rooms, the architect might tell you you have this tiny little mechanical room to work with, or they might say you have an entire floor on the 10th floor, but you don't have any mechanical rooms throughout the space. That's going to limit which piece of equipment you can use. And, it might even just tell you that you got to go with a central air handler that ducts down or something like that. First costs, your owner might be looking to save money at every instance. You will have a variety of owners. You could have, hedge funds and financial groups that have money to spend, or you might be dealing with your mom and pop retail store whose entire bottom line is based on the one store. And those are very different first costs that you have to keep in mind when you're selecting the pieces of equipment. If the cost is required to be low, you want to keep it as simple as possible. The number of zones and the diversity, um, if you have one large space, you can probably get away with one piece of equipment. But if you have many, many different zones, you might have a swimming pool or like a training room, a gym, an office space. All of them require different temperatures, different humidities, um, and they might be located on different floors. So you have to keep in mind that whatever system you choose has to be able to accommodate all of those. Utilities, this day and age, we have electrification. Sometimes natural gas is not an option anymore. How do we get heat? We got to use heat pumps. We got to use resistance heat. That just might eliminate some of your options right there. But if you can use natural gas, maybe that's the easiest solution too in a packaged rooftop unit. Same thing with A2L refrigerants. We're going through the phase downs. VRF system might not be the best option for you if you have tiny rooms and long refrigerant pipes. You don't want to have a system that might have an A2L refrigerant risk. Maybe owners are more conscious of that. Sometimes you can get away with it by connecting your spaces, but maybe there's just another better solution than using VRF. Maybe you just use a packaged rooftop unit or use a packaged PTAC. Your building size and your heat load, you could have a massive campus. You're automatically, eliminating your PTAC. That's not going to work for a massive campus. A packaged rooftop, if you have two buildings, you're not sending air underground or air from one building to the other. You're going to either be using chilled water or condenser water to get that, or refrigerant. Another important one that may be overlooked is end user facility staff. Is there someone on site to overlook and maintain this equipment? If there's no one going to be there at your mom and pop shop, everyone leaves at 5 o'clock when the store closes. You can't have a complicated piece of equipment that needs to be, overseen every part of the day. But if you have a huge building with building engineers or campus engineers that's on site 24/7 to handle that, you can go ahead and have a chiller. You can have compressors or fans over 15 horsepower that require in New York City a 24/7 on-site engineer. And then into the last two, redundancy, reliability, and energy efficiency. These can be balanced a lot of times when cost is not really, or upfront cost is not really a constraint, but they want to save money year over year, get the ROI on their equipment. They're going to want to have very energy efficient equipment. And then another constraint, in data centers, we're seeing all the time that you need to have the redundancy. If any part of that system goes down, you're going to be in trouble. So they want to have a backup system online immediately that can pick right up if the other system fails. And now these are just 10. We kind of just dove into all of these, but I'm sure you can come up with a dozen to 2 dozen more constraints depending on the project. These are just 10 of the more common ones that we see. And if you go through this list, you'll very likely come out with only one or two options at the end. So now that we've covered some of the constraints and gone over what questions we should be asking, let's take a look at some actual examples and some projects. We'll spend a little bit of time on these because there's lots of discussion in this. It's not a simple process. So here it is restated. What are the dominant constraints? That's really what we're looking for. You might have an owner who says, we want to save cost. Everyone wants to save cost. But if they're operating a facility that requires redundancy and mission critical, it can never go down, that constraint is more dominant than the cost savings. I'm sure the owner wants you to be as cost conscious as possible, but if you need to have a second redundant system, that is going to be the dominant constraint. Same thing with, where can we put the equipment? That is usually one of the more dominant constraints as well, because you might not have roof space to put it. You might not have a mechanical room to put it. You might have to put an individual unit in every room. So your job as the designer and the engineer is to figure out what are my dominant constraints and mapping that to a piece of equipment that actually works with that. It's another way of saying how many loops do we need, which loops do we want to utilize, and how can we keep this as simple as possible. So here's our first example. It's an open retail space with 16,000 square feet and one big open area. You can imagine it as a very tiny Walmart if you want, or your mom and pop's retail store, clothing store if you want. So I kind of went through and threw down some of the dominant constraints for this project. It's one large open space. There's no mechanical room that you can put equipment in. It's a single floor building. Your mom and pop shop is not going to have an on-site facility staff. Uh, and because it's a clothing store, there's no major sources of internal heat like you might have, in a data center where there's heat generated at a crazy scale. It's just clothing, people, and the lights. And mom and pop shops always look for low first cost. They do not need to be spending an exorbitant amount of money on a system. They just want it to be as simple as possible. So we can ask more of those questions. Maybe A2L refrigerant limit is not as big of a constraint here. Refrigerant limits are primarily, it's going to be dominant in small rooms. So we have one large open space. That's not even going to be an issue for us here. Redundancy, they don't need redundancy. They just want the one unit. They don't need the extra cost. And energy efficiency, while it's important to them in their day-to-day operational, it's not a dominant constraint. They just want this system to function so their customers are happy and they have a facility that can maintain the temperature they need. But our dominant constraints are listed on the left side. So really and we'll go through this exact process in all of our presentations and with the specific piece of equipment. So like next week, we're going to talk about VRF and we're going to apply that specifically to multiple different types of buildings and say, does this work or doesn't this work? But for this week, we have an open tool chest. We can use whatever we want here, but many of the times we will be reaching into our tool chest and be using rooftop units. So if you can use a rooftop units, these are super cost effective. They work great for places where you don't have huge heat loads and you don't need to have a lot of maintenance. It's just install it and you forget about it and it works great. So because it's a single floor building, the roof is a great place to put equipment. And it's one large open space. We don't need to worry about zoning it out, right? We don't necessarily need to have an individual unit in every room because it is just one large room. So if we stick rooftop units on the roof, we're just going to need ductwork, crane it onto the roof, and a thermostat on the wall to control it. So this situation is only two loops. It's air side and refrigeration. We're going to reject the heat directly into the atmosphere, and we're going to be sending our cold supply air throughout the space. As I said, rooftop units are great. So if you can find an excuse to use them, they're probably one of the most cost-effective ways to cool and heat a office or commercial space. So our example number 2 is much larger. We have 80,000 square feet. It's 6 stories, and it's a multi-tenant office. We can ask ourselves all these questions. We have multiple zones and diversity as one of our dominant constraints. You're going to have every tenant is going to have multiple offices, multiple spaces. They might have conference rooms. They're going to have IT rooms. They might have a kitchen space. And you want every office or every group of office to have its own temperature controls. So if someone runs cold, they can change their temperature, and someone runs warm, they can, make it a little colder in there. So you're going to have multiple zones. You're going to have diversity across them. And in this particular building, there's no mechanical room per floor. That is a big constraint here. There is an on-site facility staff in case that's needed. Another constraint is the architect is telling you we need to have 10-foot ceilings and there's only a 12-foot slab to slab. This happens all the time. You got to be conscious of how much space you're taking up when we pick our piece of equipment. This owner wants to have a moderate first cost. They understand this is going to be costly, but they know and they want to have electrification targets. They know they want energy efficient equipment. They want this to run smoothly after it's installed, and they're going to have a low operational cost on utilities. So for our project, these are our constraints. So how do we pick a piece of equipment? You know, of these dominant constraints, these four red ones are giving us clues on what we can use. So if we have multiple zones and diversity, VRF pops up right away. You could have rooftop units too. But since this is a 6-story multi-tenant building, maybe running ductwork from the roof down to the ground floor doesn't make sense. You don't have the amount of shaft space. Your architect already squeezed you on your ceilings. They're going to probably squeeze you on your shaft space to run your ductwork up and down the building. VRF is a great way if you have limited space, because all you're running between floors is your refrigerant piping, which can be, a quarter, 2 inches. It could be half an inch up to 2.5 inches. And, with a little bit of insulation on it, it's much, much smaller than, your 40 by 40 riser that might have to run up and down the building. Another thing VRF is great with is low ceilings and plenums. You can stick a high wall indoor piece of equipment into and on the wall in every room, and that can serve that space. And you don't have any ductwork. You don't have to take up ceiling space, and your architect is very happy that you are not compromising their ceiling heights. And the other thing is VRF is very energy efficient. These things modulate. They're super smart, and they, with all the electrification and saving money on operation, this is going to be an awesome solution, especially at part loads, with the modulation that it can do. So for our 80-story, 80,000 square feet, 6-story multi-tenant office, in this situation, we'll probably go with the VRF system, right? We don't have any mechanical room and we have low ceiling heights. Now we'll take the same office building, but your architect says, okay, fine, we're going to give you a central mechanical room on every floor. And we have actually much higher ceilings than we thought, or slab to slab than we thought. So you have more space in your ceilings to run ductwork. So this owner said, we don't want to use A2L. We're conscious of that. We understand that, there are lots of regulations going into place. And while all of that is hashed out and there are many great ways to do it with VRF, the owner just maybe doesn't want to do it. So what are we looking for in this building now? Maybe with our central mechanical rooms, we can just use a large air handler in those central mechanical rooms, and we can distribute our ductwork throughout the space. This is a very, very common use in New York City. Many times your office floors will have a central mechanical room on each floor where you get chilled water from the building. You get to select the air handler and you place it in the mechanical room as a floor mounted unit. It transfers all of your heat throughout your space. You can zone it out however you need with VAVs. Everyone gets a thermostat. And this is just like rooftop units, this is a very powerful tool in your tool chest in New York City. Especially, of course, you have to have, for this New York City application, a chilled water. You have to have chilled water. So you can either get air cooled or water cooled. This image here is an air cooled modular chiller. This thing sits on the roof and rejects the heat directly to the atmosphere. And another thing too is because we're using chilled water, there's no A2L refrigerant in this space, right? You don't have to worry about concentration limits. You just are running water. Water is non-flammable, and you don't have any worry about all of the strategies that you have to implement with A2L and VRF. So our last example here is a hospital or a campus. It's 500,000 square feet campus. You are operating 24/7. A hospital has to be operating. It has to be very reliable, very various forms of redundancy. It can never go down. This is a life safety issue for anyone who's worked on a hospital or medical facility knows that you have to make sure that these systems operate all the time. So that kind of gives you one clue. That becomes a dominant constraint. You're going to have on a 500,000 square foot campus large distances to move your heat. And as I said earlier, ductwork may not be the best strategy, especially in a 500,000 square foot campus. You're not running ducts that distance. It just is infeasible. So we're going to run, or you would like to run, water throughout your space. Another constraint that you have with hospitals or campuses is large heat loads. Just with the size and scale, you're going to have huge heat loads. You need to have equipment that can handle it. A little PTAC can only go up to like 2 tons. You're not going to be able, how many PTACs are you going to need to cool down 500,000 square feet? That just quickly gets out of scale for cost. And maybe that's not the way we want to move. You have an on-site facility staff here. This campus is operating 24/7. There's engineers are there to help if anything goes down and maintain the system to make sure that redundancy and that operation is maintained throughout your day at 24/7. And energy efficiency, right? If you're running 24/7, you're going to be just throwing money out the window if this thing is burning cash, burning energy, burning natural gas and electricity. So you want to have equipment that is going to be energy efficient. Usually that comes with a little bit higher capital cost, upfront cost, but then you get return on it with lower operation. So with this huge campus, they know they're spending a lot of money. This has to work the way they need it to. So in this situation, we're moving the heat the long distances, huge heat loads, and they want energy efficiency. You reach into your tool chest. What do you got? We have all 5 loops at play here, right? We're going to have a cooling tower. This is just one way to do it. You can do it many ways, but we're going to have a cooling tower to reject our heat outside. We're going to have a water-cooled chiller inside, and you're going to have your air handling unit inside. So this is just one way to do it, but because we're moving heat long distances and you need the energy efficiency, having a water-cooled chiller is a great way to do that. You pump the water throughout the campus. Every building, every floor gets its own chilled water. And your water-cooled chiller is super efficient. So you're going to get all that energy savings from having energy efficient equipment. And your cooling tower sits outside. You don't have to have that sitting in your room. That can sit outside on the roof or on grade, wherever it makes sense for you. But those cooling towers they're dense, right? You can have a lot of tonnage in a small footprint, which is one of their powerful pros that you can use. So I'm coming towards the end of the presentation here. So what do we go over today? What do we want to take away? In the beginning, I promised you 4 things. You are going to learn how to describe how heat transfer systems, or actually heat transfer equipment, moves heat in and out of a commercial space, right? That's the goal of all the industry that we work in. We have to move our heat out of our commercial space into the ambient air. The second promise was that you'll know what the 5 loops are. All right, we went over each of those 5. They're listed at the bottom of the screen here. Your air side, your chilled water, refrigeration, heat rejection, and your controls loops are all powerful ways to move heat, right? There, you reach into your tool chest, and every one of those pieces of equipment is going to utilize 1, 2, or a combination of these system loops. The third promise was, what project constraints are going to drive our decisions on which pieces of equipment we're going to use, right? So every project is unique. You should always do the diligence of asking yourself those questions, and there's always many other ones, but those 10 are a great place to start. You'll eliminate many options that won't even work for you. And that's just due diligence as an engineer. You got to ask these questions. And lastly, the selection, right? Once you have those dominant constraints listed out, you get to just pick which piece of equipment you want to use at that point. And really the goal of our whole series here is, um, you know, trying to help you understand the selection part of this 4-step process, right? You're gonna be able to quickly determine which project constraints are the dominant ones, but how do you then select the piece of equipment, right? We're gonna go through in this series, the strengths and weaknesses of every type of equipment. Today's presentation was an overview, just so people can understand where we actually live in the HVAC industry. Um, but as equipment salespeople on my team, we want to help you guys have successful projects, right? You might reach out to us and ask for a selection. We'll help you determine which piece of equipment works best. So this presentation is PDH. There's 3 questions at the end here, and we'll kind of quickly run through them. Which one of these is not part of the 5 system loops? We have A, energy consumption, B, air side, C, chilled water, or D, controls. I'll give you a second to think about it. Or you can just look at the bottom of the screen and figure out that the answer is A. Energy consumption is not one of the 5 loops. Airside, chilled water, and controls are. Question 2. The refrigeration cycle is necessary because A, building code mandates it. B, heat does not flow cold to hot naturally. C, it significantly reduces operating noise. Or D, improves visual aesthetics of equipment. So I'll give you guys a second to think about it. And the answer is B. Heat does not flow naturally cold to hot. So we need to add in work, right? That's what our refrigeration cycle is there for. We input work to move up the gradient, right? We want to push that cold or push the heat up the gradient from cold to hot. And our last question, this is an example again, a small single tenant retail building with a tight schedule and minimal facility staff is a best fit for a chilled water plant, packaged rooftop units, a geothermal field, and a custom built up air handler and chillers. So I'll give you guys a second to think about it. You have a small single tenant retail building. And the answer is B, packaged rooftop units sized for zones, right? We don't want to go overkill here with chilled water plant. Geothermal plant is going to be way out of the budget, and custom built up air handlers and chillers are, while they could work, are going to be pricey for the custom built up ones. So that's it. Today's topic is complete. We went over the fundamentals, and next session, next Thursday at noon, we're going to be going over topic number 2, which is VRF fundamentals. So thank you guys for all joining. I know we finished a few minutes early, but this is just fundamentals. As we go into it a little bit deeper in specific equipment, we're going to be pushing into the hour. So I appreciate everyone's time today. Thank you very much for joining. You'll get an email after this presentation is done with the recording. So thank you very much, everybody.